It's my great pleasure to introduce Turbo Ho, visiting from CSU Northridge, who will tell us about 0-1 laws for finitely presented structures.
Hello, it's great to be back to Madison and the Midwest. This is a joint project with Johanna Franklin and Julia Knight. I think I see Julia here. Hello. I'm not sure if Johanna's here because I can only see 4 people. But yeah. So this is going to be about the 0-1 laws for finitely presented structure, and you've probably seen 0-1 laws in some of its forms. And let's see a very classical one. So this is from graph theory. So this is a Erdős-Rényi random graph. What it is that it's a graph, or really technically a random variable who takes value as a graph. It takes 2 input as parameters, N and P. N is basically the number of vertices, and P is just a probability between 0 and 1. And what it does is that you build this on, well, n vertices. We usually call them 0 to n minus 1. And now you have n choose 2 many places where you could possibly place an edge. And so for each of them, you flip a coin with, probability B being head, 1 minus B being a tail. If it's a head, you add an edge, otherwise you don't, and then you do this n choose 2 many times. And then you're going to get a graph. So this is called the random graph model. And a theorem by Fagin is that if you have a first order sentence in the language of graphs, so just the edge relation, then you have the following 0-1 law, is that if you look at the probability of such a graph satisfying this first order sentence, and this probability always go to 0 or 1 when the number of vertices n goes to infinity. And of course, you need P to be strictly between 0 and 1. If it's 0 or 1, it's not very interesting. Otherwise, you can have P to be anything you want. And a consequence of this is actually, if you do this, say, on omega, you're going to have this what's called the random graph. That's got called G omega P, and the part of the theorem actually says that this limiting probability goes to 1, actually if and only if the sentence is just true in the infinite version of the random graph. And it actually turns out that as P is strictly between 0 and 1, the infinite version are all isomorphic. So this is sort of the classical example. But here you see the randomness are on the edges. So you really need that to, sort of be a relation, because a relational language, because if it's a function, then, well, if you build it as a relation, you're almost always not going to actually get a function. So that's one thing that we're trying to do here, is that we were trying to figure out how to do that if you don't have a relational language. So one common example that people outside of logic has done is random groups. I'll tell you a little bit about random groups here. This is originated in 1987, given by Gromov. We're not going to get into the glory detail of the definition of random groups. But you can actually prove that, for instance, a random group using the previous sort of limiting probability idea, you can show that the probability of it being infinite goes to 1 if certain parameter goes to infinity, and the probability, of course, being torsion-free, being non-abelian, being hyperbolic, being one-ended, and the probability of the probability of it having a lot of free subgroups, these probability all goes to 1. And so one thing that we see here is that these are all adjectives. They're also true for the free group, which in some sense is sort of the free object in the category of groups. So one thing that I highlighted here, one-ended, that is not true for free groups, but all the other ones, the black ones, are true for free groups. So this leads to the question is that, can you formalize this? And before we can even do that, we need to actually look at the free group, because in the case of random groups, no matter what your P is, they're all isomorphic. But for free groups, there is a parameter, namely the rank of the free group, even if you're looking at a finitely generated one. And it is, well, first, they're, of course, not isomorphic. But second is that, do they even have a common theory? And that was actually the Tarski's problem. So Tarski's problem have two parts. The first part, which is the part that's relevant here, is whether two finally generated free groups of different rank have the same theory. And the second part is, of course, there's a natural embedding, is that embedding elementary. This is solved by Sela and Kolenkovich and Myasnikov in 2006. And they show that any non-abelian free groups of different rank, they're all elementary equivalent. So that means that here it makes sense to compare the limiting theory of a random group with the theory. So now we know it's just one common theory of the free groups of finite rank. So that's what Knight conjecture is that a first order sentence is true in a free group if and only if it is true in a random group. Okay, so this is basically sort of you take the 0-1 law for graphs and then you try to formalize the same thing but now for groups. Okay, we will say a little bit more about how you actually build the random groups, because as we've seen, it's not so sort of straightforward how you're going to transport the graph theory version. There are some partial success in this conjecture. In 2021, Kolenkovich and Sklinos showed that a universal first order sentence, the first sentence that is universal, so the keyword here is universal, satisfies the 0-1 law. Namely, it is true in the free group if and only if it's true in a random. For higher complexity, this is still open. Okay. So now what we want to do is we want to, try to do this for things that are not groups, because, well, the group question seems to be hard, but can you ask the same question for other structures? So universal algebra will come in a little bit at some point, but first let's look at a toy example. So let's assume that we have a language with just two unary functions. We're going to call that S and S inverse. So as you can expect, we're going to say the theory says that S and S inverse are inverse functions. So that means that, for all x, S inverse equals to x, and for all S inverse S of x equals to x. Okay, and now what we're going to do is we're going to consider a single generator A. So I don't want to go there yet. So if we consider a single generator, then what we really do is that you can look at what's called the free structure. That is really just a term algebra of this, one generator and this language and the theory. So you're going to have, how do I write? Okay. So you're going to have this A over here, and then of course you have S of A, and then you have S squared of A, and then the S inverse is going to go the other direction. So you have this S inverse of A and so on. Right. So basically the free structure here is really just a Z shape. Okay. All right, so that's straightforward. So now let's try to look at quotients. So this is also how Gromov built the random group, is that you start with the free structure. In the case of groups, it's the free group, and then you try to randomly take some relations. But here the relation really is an identity on saying, oh, these element in the group equals to that element in the group. So this is what we're going to do. So we're going to take what's called a random identity, and basically what we do is that on the left hand side of the identity we take a random term. Right, so what does the term in this case look like? It just looks like S to some epsilon, where epsilon could be positive or -1. And I have a bunch of those, many of them in particular on the left. And the only thing I can apply them on is the only generator I have, so it's A. And then I do the same thing on the right, right? So we're really just say two random terms are equal. And of course, the random terms corresponds to random elements in the free structure. And if I say they're equal, then, well, in this case, because S and S inverse are inverse functions, it's not very hard to, cancel the positive and -1s out and move all of them to one side. That's straightforward to show this is always equivalent to S to the K for some integer K of A equals A. Okay. So what you end up getting here is what we call a presentation. So the I shouldn't have a bar there. But this is a presentation. This is really just the left-hand side of the presentation tells you what's the generator. The right-hand side tells you what's the identity that you have to satisfy. In this case, you only have one identity. In most of the talk, we will only look at one identity, but you could potentially do more than one. And what this is just the freest structure where this identity is satisfied. So of course, the identity is going to imply other things, right? So if you know as to the k of a equals to a, then you know as to the k plus 1 of a equals to s of a, right? So it's going to imply other things. So really what you're saying is that two terms are equal if the original theory T plus this identity proves those two terms are equal. Then you can actually show that, oh, this is a well-defined thing, and that will form a structure in this theory. And in this case, it's fairly straightforward to see that, well, you're going to start with A, and then you're going to have your S of A, and so on. And then you're going to have your Sk minus 1 of A. But then if you go one step to the right, you're going to go all the way back to A. So basically, you have a cycle of size K. Okay, so here, this is the quotient structure. The quotient structure will look like a cycle of size K. And of course, remember, the K is a random variable. It came from, you chose the random terms and how they cancel, right? But this is what the quotient structure will look like. And then it's not very hard. Then we have to look a little bit at K, right? So K depends on I and J, or really it's a random thing, but the I and J's are really the sort of the input parameters, right? And so when I goes larger and larger, well, you're very unlikely to have the power sum, the exponent sum on the left-hand side equals to the exponent sum on the right-hand side. So basically what happens is that when I and J goes to infinity, I minus, or rather, I guess it is just K, which equals to the sum of the epsilon I minus the sum of the epsilon I prime. This also, or rather the actual value of this also goes to infinity. Not exactly at the same rate, but it well goes to infinity. Okay. All right. So this is the situation is that, so now we start with the free structure, which is a Z chain, and then the quotient structure will look like larger and larger cycles. Right. So if you look at it from far enough, then you say, oh, they probably have the same theory, and you can prove it. So this is how you prove it. So there's a lemma, which is, well, if you're a graduate student, this is about maybe a qualifying exam problem, that you can show that over this theory T, every sentence is equivalent to a Boolean combination of two particular kind of sentences. The first kind just says that there are m disjoint cycles of size n. And here, of course, if we have a cycle, we only have one. But in general, any structure over this theory, this is true. And then there's a second kind, which is basically saying whether you have a chain of length up to, at least n or not. So it turns out that you can show every sentence is a Boolean combination of these two. So all you need to do is to show the Theorem law holds on these two kinds of sentences. And that becomes straightforward because as your K goes to infinity, for a fixed m and a fixed n, the first sentence is always going to be false. Well, unless n equals to 0, right? Because the cycle is going to get larger and larger. For a fixed n, eventually you're not going to have a cycle of size n. For the second one, eventually is going to be true. And of course, this coincides exactly with the true and false of these sentences in the free structure, which is a Z chain. So you get a theorem saying that for every sentence, first order sentence B is true in a one generated random structure in this what's called in this category, if and only if it is true in the one generated free structure, which is just a Z chain. Okay, so this is sort of how these kind of games are played. So formally, we borrow definitions from universal algebra to make this all sort of formal. So first we need to have a class, and the class we're going to be looking at are called algebraic varieties or equational classes. They are the same thing proven by Burkhoff. We are going to call them algebraic varieties, but we're actually going to take the definition for equational classes because that's what's more convenient for us. And here we go. So here's the definition. First, you define the language as algebraic if it has no relational symbols, so you allow only functions and constants. And then you say a class of structure over an algebraic language is an algebraic variety if you have an axiom for this class where every axiom looks like for all x, some term on x equals to some other term on x. Okay, so for instance, we'll look at the example. And then in such a structure, you can always define what's the free structure and what's the quotient structure. So a free structure is basically just the term algebra modulo whatever the axioms tell you are equal. Okay, and then the presentation, this is really just the quotient structure, has two parts. The generator, usually we're going to fix the generator when we think about an algebraic variety, and R is the identity. The identity must look like the form some term on A equals to some other term on A. Okay. So again, we're really just picking two things in the free algebra and say, oh, you're the same. And then you take the freest structure. So this is the same definition, is that you look at what you can prove from the theory and an identity on and this identity on A, and that's it. Right? You can prove that actually gives you a structure. So some examples, the previous example, the toy example, where you just have S and S inverse, that is a algebraic variety, and groups and rings are also algebraic varieties. So this is the sort of the setting we're going to be working. And then how does the random come in? How do we make that formal? So we're going to look at for a fixed property, usually a first order sentence P. We're going to define PL to be the probability that this quotient AR satisfies B for a randomly chosen R. And the way we're going to randomly choose R is basically you look at, roughly speaking, you look at all the identities up to a certain length. So you look at all R with the length of R less than or equal to L. Okay, and then call this set, S. And what you do is that the probability up to L of B just equals to the R's in S such that A bar R models B, and then this is the bottom is just the size of S. Okay, so you basically just look at fix a length L. That's what the subscript is doing. You look at all the identities up to length L, and of course that's a finite number of identities. And then you just ask, okay, for which of you, when you take the quotient, the corresponding quotient will actually satisfy B. Right, so that's what this is. And this is actually exactly what Gromov did, but well, in a group case. So up to rescaling the length a little bit. Okay, so this is what you do. And then the definition then follows naturally. You say a random structure in this variety B satisfies this formula B this sentence B if PL of B equals to 1, right? So the limiting density actually equals to 1, and you say it doesn't satisfy or you can really just prove it satisfies not B if this equals to 0. And then you say a variety satisfies the 0 law if for every sentence this probability is either 0 or 1. And you also say, because in the previous example, we see that they not only is always 0 and 1, the truthness actually lines up with the truthness in the free structure. So you can go one step further and ask, is that always true? Turns out these two are two different notions, so we're going to call this, for the purpose of this talk, a strong 0-1 form. Okay, so it's a little bit stronger. Okay. So first observation is that this really just coincides with Gromov's random groups model, so we're not, just coming up with a completely new thing that really sort of is an extension of what group theorists have been doing. And the second thing is, well, this is just using this language, we can say that the variety of a pair of inverse functions satisfies the strong theorem. Okay. Any questions so far? That's the basic stuff. All right. So now what do we do? So of course, you have a notion, you want to classify it. So there are obviously three possible cases. You can just not have a limiting theory. That's of course possible, right? So far we don't have an example, but of course that's possible. The second one is you have the non-strong zero-one law, right? Which means that you satisfy the zero-one law, but for some reason the limiting theory is actually not the limiting theory. Sorry, not the theory of the free structure. And then of course you have the strong case. So those are the three possibilities. It turns out that all three possibilities are actually possible. We're going to look at some examples. So before we go into the example, I want to point out there are sort of two features or two ingredients of the proof for the bijective structure, so the S and S inverse. The first ingredient is that random identities cannot be detected locally. What I mean by this is, roughly speaking, when in that particular example, when I and j goes to infinity, right, namely the length of the identity gets longer and longer, the k, sort of the defining parameter of the quotient structure, also goes to infinity. Right, so locally, your quotient looks like the free structure just because, well, some parameter goes to infinity. This is in a very loose sense. Okay, and then the second, of course, is saying that every sentence is equivalent to a Boolean combination. But more, these Boolean combinations are local in a sense, right? So these sentences are local so that they're not actually able to detect whether you are in the quotient or not, right? So they're not able to tell whether you're in a free structure or in a quotient, and hence you just end up getting the same theory. And that's sort of how the proof goes. So we're going to first look at the first one, is sort of the random identity cannot be detected locally, and we're going to look at a few examples and see how this could possibly fail. There are many ways this can fail, but one way this fails is, well, you look at an even easier example. You look at only one unary function and no theory, no answers. So what happens? So here, the free structure is going to be an N chain, right? Because you start, or omega chain, right? Because you start with a, so for the rest of the talk, we're going to concentrate on only one generator. Again, you can do it with more generators, but one generator already sort of have an interesting story. So you start with A, right? And then you have f of A, and then you have f squared of A, and so on. So this is the free structure. Is just an omega chain. Okay, and then if you look at a quotient structure, then what you're going to say is, well, the left-hand side must just look like f to some power of A, and the right-hand side also look like some f to some power of A. So you just end up having f to the I of A equals to f to the j of A. Now, this is not bijective, so you cannot cancel out the i's and j's. So you really just end up getting, you have A, and then say I is less than J, right? So this is f to the I of A, and then you're going to go a few more steps. And then when you get to f to the J minus 1 over A, you're going to loop back like that. Okay? So these are all sort of directed edges. So here you see there's actually something very easy to tell whether you're in a quotient or not. Namely, you see this special point over here, right? This is a point where the function f is non-injective. And of course, f is going to be injected in the free structure. So let's call this point B. Right? So it turns out that what you can prove is that you can prove that the theory of this, I don't know how to write this, but the theory of this limits to the theory of the following structure is that you have an omega chain here, and then you have two omega chain coming in like that. So, sorry, omega star chain coming in like that, where you have one omega chain going out. And this point, of course, is the point B. Okay. Is that clear enough on that?
It should be omega then?
Yeah, on the right is omega. Here is too much. That's omega. Yeah. So we can actually show that in this case, you do have a 0-1 law, but the 0-1 law, because of exactly this non-injective business, is not going to line up with the theory of the free structure, which is an omega chain, on which F will be injected. So you can actually show that well, this quotient structure will, as ij goes to infinity, will limit to this bottom structure, because you can imagine that the distance between A and B gets further and further away, and then this sort of loop that you get from the I and j being equal also gets larger and larger. And so you're not able to see that, or rather in the limit that just becomes omega star chains and omega chains. Okay. So that's one possible situation where you have a weak or non-strong 0-1 law. And you can also just not have 0-1 law at all. For this one, this is where you have two unary function symbols and again, no theory. And this again, what breaks really is injective. So the free structure again will look like the free structure will basically look like a complete binary tree, right? Where going left is basically F and going right is G, and then you can keep doing that. However, when you take a quotient structure, there may be a few possibilities, because depending on how the left-hand side and the right-hand side of your identity started, you could be looking at F and then some word U of A equals to F, and then some other word U prime of A, or it could be F and G, or it could be G and F and G and G. And then it's, well, if you just count how many identities there are, you see each of these will have 1/4 possibility of happening. But for instance, if you look at the first case, this has 1/4 possibility of happening. And in the limit, U is extremely unlikely to be equal to U prime, right? If you're just quotienting out this. And so that means that you're going to have two different things, namely U of A and U prime of A, both of which their F image is the same thing. So that will break injectivity on F. But if you are in any one of the other cases, it will not break injectivity on F. So in this case, F is non-injective. While in those three cases, F is injected in the quotient. Okay? So that will directly give you a sentence, namely the sentence saying, for all x and y, x equals to y implies f of x equals f of y. So the sentence saying f is injective is not going to satisfy the 0-1 law. Right? Make sense? All right. So now we have all three possibilities. So the question is now, well, what happens next, right? Is there a nice way of giving sufficient or necessary conditions for these to happen? There's another example here. I'll just say this in words. Here's a quick example where if you try to do more than one identity, the story actually becomes much more complicated. Because here, if you have two identities, so this is the same bijective structure example. If you have two identities, you're looking at s to the k of x equals to x, and s to the k prime of x equals to x. So if you have a presentation where both of these identities are true, then it will actually look like a, let's call that G cycle, where G is an integer, where G equals to the GCD of K and K prime. So this is sort of a straightforward Euclidean algorithm proof. But now the point is that if you ask, for instance, whether the quotient structure is trivial or not, namely whether s of x equals to x or not, then you actually end up asking whether k and k prime are co-prime or not. And that that probability is actually strictly between 0 and 1, and it's a funny number. There are some parity concerns, but if we don't get in there, then the number is basically 1 over zeta of 2, where zeta is the Riemann zeta function. And that's 6 over pi squared. So, well, there's some funny number theory thing going on, and we're not going to go there. Okay, so this is just a quick illustration of the story is actually more complicated, much more complicated if you have more identities. Immediately get much more complicated. Okay, so now we're going to just look at, so you have seen that we concentrate on the cases where we only have unary functions. And the justification is basically if you have even binary functions, you start getting groups, and that's a hard question. So we're trying to avoid that. And then this is a justification of just looking at one identity in some sense, because if you do 2, it's already a sort of a different kind of question. Okay. So you see this detected locally in the previous 2 cases, they both fail sort of because you break injectivity, and that's something you can see locally, right? Namely, I have 2 things that got, like locally, I have 2 edges going into the same place, right? So that's roughly how, actually, yeah, one sort of very common way, actually, I almost want to say the only way that we know that this can fail. Okay. So the second thing is more interesting, and this is where we get our general theorem from. So the second ingredient going into the proof for the bijective structure is this Boolean combination of local sentences, and this actually goes back to finite model theory. Goes back to Geithman, I think in the 70s. I forgot to write down the time here, and I forgot. But basically, this is something that's actually being studied in finite model theory. So here's the setup. So here we actually need a relational language. So in the original setup, and the Geithman graph of this relational language is really just the graph where V is just the universe of the structure, and you say 2 things have an edge between them if some relation holds on them, maybe with some extra inputs, right? So some R of X hold where A and B are 2 parts of 2 coordinates of X bar. If you look at this graph, then you can actually, well, if you have a finite language, then the X relation is actually definable because you just say there is this, it's a sigma 1 definable thing. And then, of course, you can then define the neighborhood. You can define distance and all that. Right? For a fixed length, you can define I am this far from that. Okay, so yeah, so those things are all definable, and we are going to look at what's called local sentences, and for that we really just means that all the quantifiers are local. So this is what we do. You say phi superscript bracket R is a local sentence, or you write a local sentence like this. If all quantifiers are for all y in a neighborhood of x, yada yada, or for, is this y in the neighborhood of x, yada yada. Okay, so such a sentence, so the radius of the neighborhood is R, and such a sentence is basically called R local. So this is sort of what we were seeing, is that in the previous examples, we were really thinking of them, because we have unary functions only, we really think of them as graphs. And we saw that all the interesting things that we are looking at are sort of local. And then you get the 82, yes. You get the theorem, which is due to Geithman, that says that if you have a relational language, then every sentence is equivalent to a Boolean combination of, well, almost local sentences. You see the first part, the alpha I part, are the local sentences. All the quantifiers are bounded in a ball. The second part is not, because you still have to be able to say, well, there are things that are far apart, and that's exactly what that's doing. So that's a very specific sort of way of not being local. Everything else is. So in our situation, so this is just that theorem again. In our situation, we are going to only look at languages with unary functions. So all the structures here really are thought of as directed graphs. And the Geisman, you can really think of all the unary functions as just a binary relation that, for every x holds exactly on one y, but it's a binary relation, and that's exactly the edge relation. And these edges are in some sense direct. Okay, so you're looking at these Geisman graphs of our structures. In our case, this alpha I to the R, because we not only have a finite language, because this really came from a functional language, all the balls are actually finite. And so what you can do is you can actually just have all the alpha i's describing just the whole ball, the whole structure within distance R from a point. So we can actually have the alpha i's to be that in our situation. Of course, the dxy is still just the usual distance on the graph. Okay. So this really is a very strong way of saying the second part of the two things that we're looking at is that in this setting of unary functions, every sentence really is just telling you local information, and the local information needs to be far apart, otherwise they overlap and there's trouble. But that doesn't. Yes.
Maybe I'm misunderstanding the definition, but this d of vi bj greater than 2r,
right?
Isn't that like a universal quantifier over?
Right. So this part is local,
okay,
and that part is not.
Yeah, so why is the second part non-local?
Like,
not asking for proof, but like, what's wrong with saying that using universal quantifier over the ball, you say that like Vj is not equal to...
This is sort of negation, right? This is really saying Vi and Vj are not of distance to R, and you're allowed to do that, but that cannot be said in a, I guess, yeah, that cannot be said in a positive local. Does that make sense?
Well, the positive part makes sense, but that wasn't part of your definition, right? Like on the previous slide, you said that the local things just involve like quantifiers.
Yeah. So I guess I said this wrong, but I'm not claiming everything is actually local.
Right.
So this is the actual theorem, which we get something a little bit less than saying everything is actually local, because I still have the non-local part that cannot be written as a Boolean combination of local. Does that make sense?
It exists out front. It's the non-local part, right?
You're
saying there is a V not in the neighborhood of the other V.
Right, yes.
If you're saying there is a V in the 2n neighborhood of the other V, it'd be local. If you're saying there is a V not in the 2n neighborhood.
Okay. Yeah, no, I think I just need to read the definition again. Yeah.
Okay.
Thanks.
Right.
Actually, while we're question, I have a question also. Why is it this fixed R? I mean, can you really get a fixed R that works for all VIs simultaneously, or pairs VI, VJ simultaneously?
Yes, you can get a fixed R for a fixed sentence. Of course, as the sentence varies, the R needs to get larger. Yeah, because roughly speaking, so if you just look at a sentence like this, if two things are, if a witness have some VI and VJ getting too close, then you just make your R larger and then just, capture both of them into just one thing, right? And then you describe that isomorphism.
Right.
So
I'm just thinking like if like a V1 and V2 being 2R apart and V1 and V3 being 3R apart or something like that. How do you now express that kind of, I don't know. Yeah, I'm being very precise.
Well, then we need to get into the.
Okay. Sorry.
Okay. So, all right. Well, any other questions? Okay. So that's the theorem. So now we can get to sort of the main result. Here is now we're going to look at some generalization of the bijective structure. So it turns out that the bijectivity, I guess, is the thing that really makes everything go. Because if you loosely speaking, this is intuition, but loosely speaking, if you don't have bijectivity, then you run into sort of the injectivity problem. We don't have a proof. We would like to have a proof, but this is what we can do is we need the bijectivity condition. But if you look at structures in this language and you probably guessed that right, I'm going to have the fi's to be inverse of fi, fi inverse to be the inverse of fi. Then an example is that if I have fi and fj commute, so if everything commutes, and I actually know their inverses, and if that is the whole theory, then you can show this satisfies the strong 0-1 law, and you can actually ignore that. And you can also drop commutativity in this case if your theory only says F1 inverse and Fi are inverse of each other, then you also get a strong 0-1 law in this case. But the question is that what if my theory says more, right? So if my theory says not just they commute and inverse, if my theory says, F1 times F2 times F3 on A equals F4 of A, is that a problem? So if you keep commutativity, that is not a problem. So here's the theorem, the sort of the general theorem. If you have Fi to Fn, you actually do not exactly need to name the inverse. All you need is you need the theory to prove that they're bijective. And you also need the theory to prove they're commutative. And the free structure is infinite. Then you can actually get the strong 0-1 law. So on any number of generators, but one identity. Okay. So again, let's just look at a very quick example, just a two-dimensional example. If you have two F1 inverse, F2 inverse, then your free structure is going to look like Z2, right? Where this is the F1 direction and that's the F2 direction. And then when you take a random identity, so say that's the origin, right? And then if you take a random identity, you're basically saying that point is the same as the identity. And so you really just roll this plane into a cylinder, but then the radius of the cylinder also grows larger and larger as your random term gets further and further away from the origin. So that's very loosely speaking what's going on, but the actual proof is a little bit more involved. But you get that, but you can actually get a little bit more. So you can actually even name the generators. You cannot have the generators mentioned in the axioms. That will actually break the 0-1 law. But if you don't do that in the theory, but after the fact you name the generators and then look at the sentences, you can still prove the 0-1 law. So the Geiselman theorem goes in here, and then of course some counting, some probability goes in here. So those are sort of the replacing the two ingredients of the very toy example that we've seen. And so some natural questions follows is the first is that what happens if we drop commutativity? We don't have a result. Loosely, I'm not sure if I'm only speaking for myself. Loosely, I believe you can drop the commutativity, but that's a little bit harder, and we don't have that. And the second is what about bijectivity? And again, I'm only speaking for myself, but loosely, I believe if you drop bijectivity, you will no longer get strong 0-1 law. Actually, I think if you have too many, well, more than one unitary functions, you probably don't even get 0-1 law. But again, that's the example that we've seen, right? Is that if you don't have injectivity, then you can actually have a chance to break injectivity, and then if you have a chance, you're probably going to break it. So that's the situation. And what else do I have? And then we have some general theorem. Let me just show you a quick general theorem. So this is a general theorem that says that well, giving one condition for the strong 0-1 law to be satisfied even after you name the generators. So this is really sort of an inductive condition. So the first bullet point basically takes care saying that, oh, the 0 on null holds on all quantifier-free stuff, and then the second one says you can do one more quantifier. So this is basically the proof sort of goes as you would expect. What's interesting is we have examples where you have varieties satisfying the first condition but not the second. We also have an example where you have varieties satisfying the second condition but not the first. We actually do not have an example where naming the generator actually breaks the 0, 1 law. Namely, all the examples we have, if it satisfies the strong 0, 1 law, then you will still have it after you name the generators. And this is another sort of natural question that you can ask, is that is this actually stronger, or you're not really breaking anything by just naming the generator always? I know I'm out of time, so I think I'll stop here.
You have more time, but you could, but. All right, well.
All right, so, well, I mean, I already, yeah, I've already, okay, I'll put the questions, I'll save the questions because I already skipped the slides. Yeah, so one more question is what happens if you do more generators and do more identities. We've seen that especially more identities makes this quite complicated. More generators seems to be more amenable. We have some result in that direction, but not a lot. More identities seems to be very hard. And what happens if you allow constants? Because so far we've only looked at functions. There are some examples where if you allow constants, you immediately break the 0, 1 law in a very strong way. There's no way to recover it. But well, depending on how you edit, maybe you can do something. But again, that's another interesting thing that if someone wants to look into this, that's a possible question. All right, I guess I'll stop since I already skipped this slide.
All right, let's thank the speaker. You can't see us too, but we're clapping for you. Any questions? Any more questions?
I have one. You have a nice condition that's sufficient condition guarantee strong 0, 1 laws.
Right.
Do you know can you think of anything that might be a condition that's sufficient for a weak 0, 1 law?
I don't think we have. There are one. I mean, we have a few like. I guess that's the slide that I skipped. For instance, this one. But this is not terribly interesting. This is basically saying when you're taking a random term, you're really just concentrating on finitely many things, then you're screwed. Because you can really just say, are these two the same? And you're going to have non-trivial probability being the same or not. So it's strictly between 0 and 1. So you break the 0 and law that way. We have a few sort of conditions like this, but nothing that looks sort of more not immediate, I guess.
Okay. Any other questions? If not, let's thank Turbo again. Thank you, Turbo. All right, I'm going to stop the recording. Generally, we can hang around for a bit.